show you how to work on problem 2 from the applied math assignment using this online tool right here. So your first step is you're going to click on this tool, and we've explored this a little bit before. Remember that when we're working with a two-dimensional system, right now we're going to be working on this problem right here where this is a two-dimensional system. When we click on the link, we have to click over to System. That's the first step. So you click over to System, and one thing that you want to observe is that the horizontal axis is labeled as X and the vertical axis is labeled as Y. We're going to try to type in this predator-prey model right now into the system. For us, our horizontal axis is N, the prey, and our vertical axis is P, the predator. So I have to think of N as X, little x, and P as little y when I use it on this resource. Okay, so here I'm going to type it all in. And I'm going to type it in just like I see it. So I have R times N. Remember, N is going to be little x minus A times little x times P, which again is little y. And then the equation for the bottom is going to be B times A times little x for N times little y for P minus M times P. And, oh, sorry, not P, little y. Right, okay. So you'll see that nothing comes up yet because I haven't put in values for the parameters, but I just wanted to show you how you would type in the equation exactly how it's laid out here. The next step, of course, is going to be to apply these parameters for all of the parameter values R, A, B, and M. So I'm going to go back to what I was doing, and where it says R, I'm going to put a 0.8. Where it says A, I'm going to put a 0.02. 0.02. For B, I'm going to put 0.75. And for A, oh, we just did that one, 0.02. And then we've got M as 0.5. Okay, now that should work. So let me hit enter. Beautiful, I see it. Remember that X and Y, for the purposes of our modeling, represent populations. And so we're not really going to be concerned with negative values for X and Y. And in fact, right here on the homework, it says adjust the axes. So it goes from 0 to 100 for both. And so here's where you can adjust the axes. We're going to put 0 and 100 for the X. And we're going to put 0 and 100 for the Y. And just to even things out, we'll use the same number of segments for each one. And there is kind of what I expected to see, which is the cyclic behavior of the vector field. If you watch our YouTube live today, sorry it got cut out. I lost the internet. But what we had done in that little bit of time is we had located two fixed points. One was at 0, 0 right here, and the other fixed point was located right here. We had solved for that in terms of the parameters. To figure out exactly where this fixed point is, go ahead and look at that YouTube live video and replace all of the parameters with the values that you see here. You see, replace all those letters R, A, M, and B with the numbers you see here, and then you would be able to find the location of the fixed point. It looks like it's around 35, 40.6, something like that. Okay, so that's just how to set up the vector fields. Then it's time to play. And playing with the vector field, you can just click anywhere, and when you click somewhere, you're going to see a trajectory. When you click somewhere, that represents you defining an initial condition, and then the resulting solution is traced out as a trajectory in the state space. Here's where you need to be really, really careful. So I hope you're listening right now. I wasn't expecting to see a swirly. I was expecting to see a closed circular kind of solution. And what I'm seeing right here in the red is actually an incorrect solution. The reason why it's wrong is because Euler's method is getting implemented with a time step of 0.1, and for the system that we've defined with the parameter values we have, that's not a low enough dt. Remember when we learned about Euler's method? Right. And you need to have a really low dt for certain systems to make sure you get the right solution. So I'm going to clear out the curve, and I'm going to show you what that same trajectory would look like if I change my dt to 0.01. Watch this. That's what I'm trying to see. Right. And so you really have to make sure that you're implementing Euler's method with a small enough dt. That's one way to solve it. Or the other way to solve it would be to implement a more advanced method. Now, I know we didn't talk about the algorithms that run these methods, but we don't really need to know how it works under the hood to be able to use it. So we can just click on one of these improved methods and we'll get better behavior and not have to use such a little dt. Why would I bother when using a little dt gets me by? Here's the issue. If you use too little of a dt, like 0, 0, 1, it doesn't go very far, you see, because it's limited by the amount of iterations that it's going to use to implement the curve. And so when I used a dt of 0.01 with Euler's method, I can see that it went around, but you see this little gap here where it didn't close up? The reason is because it ran out of gas. It didn't want to implement it any further. It ran out of iterations, and so it didn't even give me one full cycle. That's not very useful. Now look what happens if you use something more advanced, like the RK4. RK4 is kind of a Runge cut of 4 is a standard numerical algorithm to solve differential equations. And so look what happens if I try it again with the same dt. Let's see if it makes it all the way around without running out of gas. Sure. Oh, no, it didn't. It didn't. You see, it's still, there's just not good. So here's what I'm going to do. I'm going to try it again with a bigger dt. Because the advantage to using a more advanced method is that it's going to work more accurately even when you have a higher dt. So now I'm going to click on it, and look, it has everything I want. It has the closed curve solution that I was expecting to see, and it also made it all the way around the bend with a dt of 0.1. Remember the solution that Euler's method gave us with a dt of 0.1? Here, let's remind ourselves. No, that's not right. If you use a more advanced method like RK4 or RK3/8 rule, there you go. You get exactly the closed curve that you're expecting. So that's really important for you to know. Make sure that you have it set on a more advanced method, and then you can use a reasonable dt and still make it all the way around the bend. Okay, so where it says to do that, it says on the vector field, it says include the trajectory for the solution with initial condition of 50 prey and 40 predators. Okay, so I don't want to actually do your homework on here for you. So for me, instead, I'm going to do maybe 60 prey and 30 predators. I'm just going to show you how to do it for a different amount of predators and prey, right? What I'm trying to show you here is that you can enter an initial condition specifically right here. So if I wanted an initial condition of like 70 prey and maybe 30 predators, I can just type in exactly the initial condition I want instead of clicking. If I was going to click, I guess I would put my cursor around 70 for the predators and around 30 for the prey. So I would probably click right around here. And you can also see on the graph, it shows you right where your cursor is right here when you kind of float your cursor over the graph. But the easiest thing to do would be to just type in the initial condition there and click submit. And so that's exactly the trajectory that I'm interested in. But for your homework, you're going to want to use 50 and 40 for the numbers. And then in part B, it says to include a time graph for the trajectory. And so right down here, if you open up this part of the system, you get a table of the values as it's implementing the chosen numerical algorithm. In this case, it's Runge cut of 3/8. And then it shows you the time series. So you can see the behavior, and it's able, not only did it make it all the way around the circle, but it actually made it all the way around 1, 2, 3, 4, 5, 6. You see, it made it all the way around the cycle about 10 times. Using the advanced rule. And so that's how you will get the time series. And a great thing about this program is that when you put your cursor on some time point in the time series, it also shows you the black dot of where that's represented on the trajectory in the above image on the state space. You see, so where I have my cursor right here, where the red curve is at its maximum, that's a maximum amount of prey. And the blue curve is kind of halfway to its maximum. That's represented on the trajectory above in the state space by that little black dot. That's about all the way to the right that it can be, and it's about halfway up on the vertical axis. Sweet, so we've got all that, and then we start to go into the questions. I probably won't go through all the questions on this video because I was just trying to make a video here to get you started. So what I want to do here is have you read the rest of the questions and try out some of this stuff. And then on Thursday, I'm going to check in with you all again, and I'm going to see how far you got and see what other questions you have about this problem. So this video right here was just to get you started. It went over parts A and B, and then I want you to go ahead and try parts C through G if you can during the week. And then let's check in again on Thursday and bring your questions to the live sessions. Hopefully it'll work a lot better. I'm sorry about the internet outage today, but I'm working with my new internet service provider to try to maintain consistent internet for everyone.